We have another example problem here. An RL charging circuit has a 60-volt battery, a 42 Henry inductor, a 24 ohm resistor, and a switch in series. Initially, the switch is open and there is no magnetic flux in the inductor. At time equals 0, the switch is closed. At what time after the switch is closed is the voltage drop across the inductor equal to 24 volts? All right, so we have a battery we know is 60 volts. It is connected to our inductor, that is 42 Henries. A resistor, that is 24 ohms. And then a switch, which I'm not going to draw the switch because I need to close the switch to in turn answer the question. So at time equals 0, this is what the circuit looks like. It tells us there is no magnetic flux in the inductor when the switch is open. That means the inductor has no energy. There was no current flowing through it before the switch was closed. So what we're trying to find is what time after this switch is closed is the inductor's voltage drop equal to, not 42, 24 volts. All right, so this is considered a charging circuit in that the current in this circuit is going to increase with time, and the energy that the inductor is storing is going to increase with time as well. So we do have our equation that represents the current in the circuit as a function of time. Now there's two ways to go about answering this question. One is not any better than the other. I'll show you both ways just so you can see. So way one, option one, or approach one. Since I have the current here, if I want to use this equation as is to find the time, I can think about the resistor, because I know the resistor's voltage drop is directly equal to the current and times the resistance. So if I know the voltage drop across the resistor at the time we're talking about, then I can just go ahead and plug that back in to the equation. But we have to be careful. The resistor at this moment in time will not have 24 volts across it. It's the inductor that has the 24 volts. But we can find out what the resistor has from Kirchhoff's loop rule. If the battery is supplying 60 volts and the inductor has 24 of it, the resistor has to have whatever's rest. So that wasn't good grammar, sorry. It has to be whatever is left. Meaning, if we take the battery voltage and subtract off what the inductor has, the resistor has the 36 volts, the difference between the two. Because the resistor and inductor voltages must add up to be that battery voltage. Okay, so 36 volts divided by our resistor is 24 ohms. This would be the current at this moment in time. So 36 divided by 24, I'm going to go ahead and just get this in a decimal form. So the moment in time we're talking about, the current is going to be 1.5 amps. That's what we will put in for I at this moment in time. We do need to know I naught as well. But remember, I naught is the maximum value the current eventually reaches. And that is when the resistor has the entire battery voltage across it. And so battery voltage divided by the resistance, 60 volts. Let me fix that. 60 volts divided by our resistance is 24 ohms. 60 divided by 24 is 2.5 amps. All right, so we can plug these into our equation. We would have 1.5 is equal to 2.5 times the quantity of 1 minus E to the negative RT over L. So I divide by my 2.5 first. To a point where my computer is complaining at me again. It's working hard today. It's 24T over 42. I do need to get the exponential by itself. Before I can take the natural log of both sides. And so I bring the e, the exponential function, to the left, and bring the 1.5 over 2.5 to the right. Now if I take the natural log of both sides, I'm going to have negative 24t over 42 equal to the natural log of 1 minus 1.5 over 2.5. Bring it over here. So our time will be negative 42 over 24 times the natural log 1 minus 1.5 over 2.5. Right, so negative 42, 24 times the natural log. I'm getting 1.6. And that will be in seconds. Perfectly wonderful way to solve this problem. There is one other way though, which I want to mention, because it might be the way you would have considered approaching the problem in the first place. So let me scroll this up a little bit. Our second option is given the value of the voltage drop across the inductor at this moment in time. We know the inductor's voltage is equal to the magnitude, because we're talking 24 volts is the magnitude. So the magnitude of this is equal to L times di dt. Now again, if you go back to the main equation, we do have a negative sign there, and that is to tell us that the induced voltage is opposing the change in flux. Here, working with numbers, we can use just the magnitude. So we know this voltage drop is 44 volts. That was given in the problem. We know the value of the inductor. The value but di dt, we have to take the derivative of this function over here that describes the current in the circuit as a function of time. If I factor through the I naught, and then think about taking the derivative of this. The first term here is just I naught. That's a constant. It represents the maximum current the circuit will eventually get to. So the derivative of that part is just 0. The derivative of the next term, we have minus I naught. The derivative of an exponential function gives us the same exponential function. But then we have to take the derivative of what's in the exponent. So this, the negative signs are going to cancel. So I'm going to have I naught times R over L times this exponent of e to the negative RT over L. So I want to put this in over here for di dt. I'm going to do it symbolically first. The magnitude of the potential difference across the inductor is equal to the value of the inductor times this derivative we just came up with. Turns out these L's cancel. The voltage drop across our inductor in this charging circuit specifically will equal, well, I naught R. I naught is the biggest the current can be, and the biggest the current can be occurs when the resistor has the entire battery voltage across it. So we can write the voltage drop across the inductor, the magnitude of it, as the battery voltage times this exponential function to the negative RT over L. Okay, we know this is 24 volts. The inductor at this time we're looking for is 24 volts. The battery voltage was 60. R, I need to go back and visit my problem again. So R is 24, L is 42. I don't need to write the 42 again, that's L. So if we scroll back down, R was 24, and then L was 42. And I want to double check that, just, yes. Okay. So I want to divide both sides by 60 so that I get my exponential function by itself. Now I can take the natural log of both sides. The natural log of 24 over 60 will be the negative 24t over 42. So this time, the time at which the inductor has a voltage of 24 volts across it, is 1.6 seconds, which is what we got before, which is a good thing because we're still solving the same problem. We're just looking at solving it a different way. Just be careful in terms of the current function represents the overall current in the circuit. The inductor's voltage, though, depends directly on the derivative of the current with respect to time, how fast the current is changing.